So this is just a review of what we have done. We looked at free vibrations in which there is no damping, like this one. So this is undamped, which means that there is no energy dissipation. The coordinate, we measure the vibration is x. The equation of motion is mx double dot plus kx equals 0. With some initial conditions, x of 0 is x0, x dot of 0 is v0. So this equation is solvable. We define the natural frequency of the system as root k over m, whose unit is radians per second, as you know. This is the natural frequency of vibration. So the free vibrations occur at the natural frequency. The solution of this equation, as you might remember, is x0 cosine omega nt plus v0 over omega n sine omega n. Okay. Which we can also write as x, the amplitude x0, let's say, cosine or sine, doesn't matter really, omega n. So the omega nt, this is n, minus a phase angle. Okay. Which means that the vibrations, frequency of free vibrations is omega n. And if we plot the vibrations, this is what we are going to get. Free vibrations, something like this. The maximum amplitude is x0, this x0, this one. And the period of oscillations from peak to peak or bottom to bottom, whatever, t, period is 2 pi over omega. That's the natural frequency. This is the period of oscillations. In seconds. Okay. And there is no damping, therefore, the amplitude does not decrease. This is the amplitude. And this is the so-called phase angle. You can find the formulas necessary for amplitude and phase angle from the previous lectures. By the way, this capital X0 and this X0 are not the same. This is small case, this is capital. Don't mix them up, okay? X0, this is X0. Small case X0. Okay, so this is the free vibrations with no damping. Let's look at the damped case as well very quickly. In the damped case, we assume viscous damping. So we have damper and mass like this. This is X, this is M, T. Our equation of motion here is mx double dot plus dx dot. Now this is extra plus x equals 0. We also have the initial conditions. X of 0 is x0. X dot of 0 is v0. No forcing, but initial conditions. this equation can be converted to x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0, okay? Where the zeta is the damping ratio, B over B critical, which is okay. Okay. This is called the damping ratio, as you might remember. And for the underdamped case, which is the most common case, where the damping ratio is between 0 and 1, the solution to our equation, this equation, becomes some x0 e to the minus zeta omega n t cosine omega d t minus the phase angle. Okay. Now note that this is the damped natural frequency. Omega d is omega n root 1 minus this is called damped. Now, if I plot again the straight line, let's say this is x of t versus t. If I plot this, what I'm going to get will be something like this. Supposedly, this has to be, it's just decreasing within an envelope like this. So this is x0 e to the minus zeta omega envelope, let's say. And inside it, you have the oscillations whose amplitude eventually decrease and become 0, depending on the value of damping. Now, here the period, excuse my poor drawing, but this is the period supposedly. This is the damped period. Td is equal to 2 pi over omega d seconds. Okay. As I said, not my drawing is not very good, but you can understand. Okay, so much for undamped vibration. Sorry, unforced vibrations, free vibrations. That is. This was just a review. I had done this before. So what I intend to do today is not this. This was just a introduction, but today I will try to look at the forced vibrations. So we'll look at the forced response of a 1 degree of freedom system. So our system is going to be the following. There is spring, there is damper, there is the mass. There is force. Okay, this is our system, but there is an external force now. So our equation of motion becomes mx double dot plus dx dot plus kx equals f of t. Now, especially important for us is the harmonic forcing, where f0 sine omega t. Okay, this is called the harmonic forcing. But why do we take the harmonic forcing and not anything else? Because harmonic forcing is, well, is very important in machinery. That's one thing. And secondly, any periodic forcing can be expressed as a sum of harmonic forcing, many harmonic forcings of multiple frequencies using Fourier series. Anyway, in this harmonic forcing, F0 is the amplitude of forcing. Force, let's say, and omega is the frequency of forcing. Omega is the omega is not the same as the natural frequency. It is just a frequency dictated by the conditions, external conditions on the system. It has nothing to do with the natural frequency. Okay, it is an external term. So our equation of motion, we will concentrate on harmonic forcing, and therefore our equation of motion is a second order differential equation of this form. There might be some initial conditions, but as we will see, we won't be caring about them. Sorry, not zero, but V0. These are the initial conditions. But the response to initial conditions is not too important. Why? Because we have a damped system. Okay. So since our system is damped, the vibrations we have is going to be in the following form. This is t. This is, let's say, x of t. What we are going to have will be, we will start from here. There might be some transients, but then eventually the response becomes a sinusoid or a cosine, doesn't matter. So there are two phases. In the first phase, the initial conditions have an effect. This region is called the transient region. And this region is called the steady state region. We are interested in the steady state region, okay? Not in the transient, because this region is it just happens for a while, but it eventually dies out. We are interested in the steady state. So we want the steady state solution. The transient solution is not too important for us because it's transitory. It is not very important. Okay. So our solution, the steady state solution, x of t, we will define it as follows. It will be some x amplitude times some sine omega t minus the phase angle. And remember, this omega is not the natural frequency, but it is the frequency of forcing. Okay, the response is at the same frequency with the frequency of forcing. And x is the amplitude, phi is the phase angle. And these are unknowns, okay? We want to find them. We want to find the amplitude and the phase angle. This is the structure of the solution we have assumed. And we will substitute this solution and try to find x and phi. Let's try to do that. Well, this is the structure of the solution. Let's take the derivatives of this. Time derivative. One derivative is of a sine is cosine omega x cosine omega t minus phi. And x double dot is the second derivative. The derivative of cosine is sine. So we substitute it into our original equation, which is this one, as you might remember. This is our original equation. Okay. So you substitute that in, and what we get is the following: minus m omega squared x plus f0 Then what we do is we have the trigonometric identities, as you might remember. Sine omega t minus phi is equal to sine omega t cosine phi minus cosine cosine omega t cosine phi. Now, this minus becomes a plus here. Sine omega t sine. You substitute them in into the above equation. And what you get is going to be the following. Okay, something like this. Okay, equals, let me write it here, equals f0 sine omega t. Well, let me also write 0 times cosine omega t. Okay. Now, sine omega t and cosine omega t cannot be zeros, so the sine omega t term, which is this one, corresponds to this, and this is the, the parentheses is the sine omega t. For cosine omega t, this is the cosine term, this is the cosine term, and they should be equal to each other. Sine terms should be equal, cosine terms should be equal. So we should be writing the following. We can write the following rather. K minus m omega squared cosine phi plus p omega sine phi times x equals f0 and minus k minus m plus p x equals. So what are we trying to find here? We are trying to find, as you might remember, we want to find expressions for x and phi. Okay. Now from the second equation, actually it is easy to, looks like it is easy to find phi because you can write the following. K minus m omega squared sine phi equals b omega cosine phi, right? X is not important, it can drop here. So we can find sine phi over cosine phi is equal to, tangent phi, therefore, is equal to b omega k minus m omega squared. So phi is simply tangent inverse of b omega over k minus m. This is one expression we have for the phase angle. Well, okay. We want to find the capital X. Let's write that equation. K minus m omega squared x cosine phi minus plus b omega x sine. We also have the other x equation. um, like this. Mhm. Let's not. There is no need for this. This is unnecessary. What we can do is, this is 0. We can use the certain trigonometric identities such as sine phi, for example, is equal to tan phi over root minus 1 plus actually tangent squared phi, etc. And once you substitute them in for sine and cosine, and simplify this. This takes a long time, but the solution for x, I will just give it to you here. Is f0 divided by something like this. Oh, okay. So this is the solution for x and phi. These are what we wanted to find. Okay. Now there is a neater way of writing things. Let me do this. We define omega n is equal to root k over n, as you know. Zeta again is b over b critical, which is b over 2 root mk, or it is equal to b over 2m omega n also. It is the same thing. Once you define these, for example, you can divide both sides of this equation into k. Inside the square root, that k becomes a k squared, etc., etc. And m over k squared, for example, is b over k squared. So x becomes something like f0 over k divided by square root of okay. Um, hmm. And m over k is 1 over omega n squared, and p over k is 2 zeta over omega n. If you substitute it, so the result we will get will be and the phase angle can be written as tangent inverse 2 zeta omega divided by so let's put them in some sort of a box. Sometimes we don't put box, sometimes we okay. As we see both x, which is x of omega, and phi, which is phi of omega, are functions of the frequency forcing omega. Okay, omega, as omega changes, x and phi change. That is the value of x and phi change. Now I can plot this, but this plot is going to be rather poor if I plot it myself. So let me try to find it from somewhere and paste it here. Let me just a second. Let me try to find the plot somewhere. Okay, this is from the book by Rao, which I use for mechanical vibrations course. This is the amplitude. This is x. This is actually equal to this part. Let me just try to write it with black. This is x over f0 over k. Okay, and this is r, which is omega over omega n. As you see, you have a family of curves with for zeta values. If damping is low, for low damping, what you get is, well, the vibrations, as the frequency of vibrations increases, at some point, the amplitude becomes very large. And that is where you have where the omega equals omega n. Here you have omega equals omega n, as you see. And when omega equals omega n, actually what you have is a resonance. To be precise, resonance occurs when omega equals omega n only when the damping is 0. But around that value, the amplitude of vibrations become very large. So the resonance is an important phenomenon, as we see from, and we can see that from our equations. Okay, let me just show it to you here. When omega equals omega n, this is 1. 1 minus 1 is 0, 0 squared. So this is what we get is x equals f0 over k divided by 1 minus square root of 0 plus 2 zeta times, or zeta times 1 squared, right? So it is square root of square is itself. So it is f0 over k over 2 zeta. Okay. So what we have really at this value will be something like this. When omega equals omega n, you have, well, this is the general for certain zeta, like zeta equals, let's say, 0.2 or something. And if zeta equals 0, amplitude, when omega equals omega n, the amplitude goes to infinity. So this is where zeta is 0. So when omega equals omega n, here, 1, the amplitude goes to infinity, which means that you are constantly adding energy to the system. And if there is some damping, the amplitude does not go to infinity, but it becomes very large, as you see. It can become very large. You know, the system vibrates at a high rate of vibration, but at a high amplitude of vibration, not rate. Okay, let's take a break at this point. I will continue. So this is, as I have said, is frequency response. What does this mean? This means that at a certain frequency value, you go and at a damping value, you go and read your amplitude, okay? In this picture, we have x over delta static. X over delta static is given here. Delta static is defined as, in that book, as the F0 over K, as I have defined, X over F0 over K. This is called the magnification factor, or the amplitude ratio, if you like. Ratio. And omega over omega n is called the frequency ratio. Okay. Now, I have given you omega equals omega n. When zeta is 0, if the damping is 0, what happens? X equals, from our equation, F0 over K divided by, well, there is a square root, but there is a square also, so it is 1 minus omega over omega n squared in absolute value. Let's look at our formulas. When omega is equal to omega, when the damping is 0, phi is, well, tangent inverse of, well, 0. Yeah, damping is 0. Yes, it's the tangent inverse of 0, right? But what is the tangent of inverse is 0 of 0? It can have two values, and it's the following. Phi is equal to, actually it might have, it is 0 when omega is less than omega n, or it is equal to 180 degrees when omega is greater than, sorry, omega n. And we see it in this picture as well. The phase angle, as you see over here, it becomes as 0 here, and it jumps to 180 degrees when zeta is 0. Okay. For other zeta values, the transition is more smooth, like this. But for 0 damping, it is either 0 or 180 degrees. And as we see, if zeta is 0 and if omega equals omega n, in this case, okay, as we see, omega equals omega over omega n is 1, 1 minus 1 is 0. We have a division by 0, it's undetermined, but x goes to infinity. The steady state amplitude goes to infinity, and this is what we call the resonance. The amplitude goes to infinity when you have undamped vibrations. Okay. So you have a resonance. There are lots of videos about resonance in the YouTube. You can check them. Yeah, and you can see that how resonance occurs. When you force a system at its natural frequency, the amplitude of vibrations become very large. You can find out about those. Now, what does this mean? Let me just try to explain this. This is 0 degrees and 180 degrees. When phi is equal to 0, this is, let's say, the yellow is F0 sine, and this, the red is X sine omega. So when the phi is 0, this is what we have, 0 degrees. They are the forcing and the response of the system are in phase. This is the forcing. The red one will be the vibration. Not a very good drawing, but you can understand the peaks and bottoms are, well, they are at the same values, okay? So there is no phase difference here. This is time. Whereas if you have 180 degrees, this is phi equals 180 degrees. They are totally out of phase. Okay, this is again F0 sine omega t. The red one is X sine omega t, let's say. Let's start this one. This is the forcing. The response is going to be out of phase. So it is completely out of phase. So it's exactly the opposite of the forcing. So this is that is, if the force goes up, the response goes down, for example, or if the force is towards the left, the response is towards the right. That is what we call out of phase. So the resonance let me draw this picture as you might see. The peak value is called this is the resonance, and it occurs at the resonant frequency. Okay, when omega equals omega s. This is X, let's say. Well, when zeta is 0, the resonant frequency is equal to the natural frequency. The maximum value, let's say, this is X resonance. But when zeta is not 0, the resonant frequency is not equal to omega n, but it is close, because you can show that this is 1 minus 2 zeta squared. Okay. If zeta is small, well, how small is small? Let's say less than 0.2 or something, okay? Then you can say that the resonant frequency is equal to, approximately equal to the natural frequency of the system. But this is not always correct, okay? There will be some error. And the resonant frequency will, for practical purposes, if you have low damping, you can always assume that it is equal to the natural frequency, but not always. And the resonant amplitude at resonance X resonant is going to be, if you derive that equation, it's F0 over K times 2 zeta root 1 minus zeta squared, okay? Now, again, when zeta is small, again, in quotes, X resonant can be approximated by F0 over K divided by 2 zeta, which I have derived about. This is the condition for omega equals omega n. Okay. But this is even larger because 1 minus zeta squared in square root is a number that is smaller than 1. So when we divide something smaller than 1, we get a larger value. But the difference might not be too big. Okay. Okay. Let me just copy this picture again. Let's copy this here. Let's keep this picture here so that we will talk about this. Okay. About this result we have obtained. First of all, as I have said, the resonant frequency is equal to the natural frequency times 1 minus 2 zeta squared, okay? And don't mix this up with the damped natural frequency. Omega d is omega n root 1 minus zeta squared, okay? They are different. Different from, let's say, omega d. So when zeta is not 0, the resonant frequency is not equal to the natural frequency, and the resonant frequency is not equal to the damped natural frequency. And omega resonant natural frequency is always, less than the natural frequency. It might not be very small, very different, but strictly talking, it is correct. Now, secondly, if the damping is small, as I have said, the resonant frequency is equal to, approximately equal to the natural frequency. Okay. And the resonant amplitude will be equal to F0 over K over zeta. Okay. Resonance occurs only at a certain value of zeta. That is, when the damping is between 0 and 0.707, when the damping is 0.707, you don't have a peak in the response. This is what you have if damping is 0.707. This is what I have drawn here. So there is no peak and there is no resonance, as you see. So below that, there is no peak in the response, and the response is smoother, well, in terms of frequency response, by the way. Because, let me write it down, for zeta greater than or equal to 0.707, the frequency response is for very large values of omega, which means omega over omega n is much larger than 1, you have, from our equations, we can see that x over f0 over k goes to 0, which means that x goes to 0, and let me write it here, phi goes to 180 degrees, or pi radians, regardless of the damping zeta. We can see it in this picture that for very high values of omega, that is around here, as you see, or here, all the values of the response go to 0, okay? Which means that if you force a system with a very high frequency input, the response is going to be very small. And the response is going to be out of phase because all the responses eventually go to 180 degrees of phase difference. Okay. So for very high frequencies, the system does not respond very well to a forcing. When omega equals omega n, the phase angle phi is 90 degrees, which is equal to pi over 2 radians actually. Again, regardless of the damping ratio. Which means that there is 90 degrees phase shift between the force and the motion. Between the force and the motion, there is a 90 degree of phase shift. And you can see it here in this picture. At all values of zeta, when omega over omega n is equal to 1, this is what you have. You see, you have exactly 90 degrees of phase shift. 90 degree of phase shift, what does this mean? If the forcing is a sinusoid, then the response is a cosine. If the forcing is a cosine, then the response is a sine. There is 90 degree of phase shift between them. Okay, actually, there was something I forgot, but let's write it here. This is kind of important. I should have written this before, actually. 6, when omega equals 0 for very low frequencies. Low frequency. Asymptote. X over f0 over k. If you look at our equation, when omega is 0, or let's look at this. This is where we are. This is where we are. Okay. You see that all of the curves start at 1. And you can find that in our equation also. So x equals 1 and phi equals 0 degrees. Again, regardless of the damping value zeta. Okay. All of our curves start at 1 and all of our curves go to 0 at high and low values. So these are the observations we have. Again, I have to emphasize that this curve is the frequency response, okay? Frequency response is not the time response. The system over the time does not make these motions. It doesn't do this. We just look at the certain frequency, look at the amplitude, and the system itself is doing a sinusoid response. The time response of the system is exactly a sinusoid. This is the time response would be something like this, okay? This is the time response. Whereas this is the frequency response. These are two different things. They might express similar things, but you know, the transition from one to the other one is not straightforward. Okay. Let me just solve a simple problem, and then I will stop for today. The next time I will just solve some problems. So just to illustrate what is. We have, let's say that a mass spring damper system like this. This is x. There is forcing f of t. M is 10 kilograms. B is 20 Newton per meter per second. K is 4,000 Newton per meter. F equals F0 sine omega t. And F0 is 100 newtons. And omega is 10 seconds. So it asks us what is x of t, the steady state response of our system. So f is equal to 100 sine 10t. Okay, we will have to find our parameters first. The natural frequency is root theorem, which is this is 4,000 divided by 10, 400, so it's 20 radians per second. The damping ratio zeta is B over B critical, or 2 root mk. Or you can write this as B over 2m omega n. M is what, 10, omega n is 20, so it's 420, so it is 0.05. Well, low damping. Okay, omega over omega n is 10 over 20, so it is 0.5, the frequency ratio. And F0 over K, the frequency thing is, F0 is 100 over 4,000, is 0.025 meters. This is the static deflection, so to say. Our response is, it's quite easy actually from here. We just have to, well, this is a simple problem, so it's easy. X of t is simply x sine omega t minus phi. Omega is the frequency of forcing. This is 10 radians per second. Okay, now it's not the natural frequency. The amplitude x is equal to, from our formula, f0 over k divided by square root of 1 minus omega squared plus so x is equal to f0 over k is 0.025 divided by 0.5 is the frequency ratio squared plus 2 times 0.5 squared. And the result is 0.0326 meters, which is 3 centimeters, okay? Amplitude of vibration. The phase angle phi is equal to tangent inverse of 2 zeta That is 3.81 degrees. This is what we get. So we found the result, 3.81, and the response is going to be x of t to this forcing is 0.03326 sine nt minus 3.81 degrees, if you like, but you have to emphasize degrees. If you actually, strictly, you should be writing radians there. So multiply it by pi and divide it by 180. Yeah. Meters. This is the response of a system to such a force. Okay, this I try to illustrate this. As I have said, the next time I'm going to solve problems, like 3 or 4 problems on vibrations, to show you how these things are. I will try to solve some of them are easy, some of them are not so easy, but some more problems. Okay, that's what I intend to do for today. So we looked at forced vibrations. We saw that the vibrations occur at the frequency of forcing. And we looked at harmonic forcing especially because it's important. And we saw that the frequency response of the system can be shown by a family of curves with zeta changing, damping ratio changing. And the remarks are given in order to explain the results we have gotten from the following diagram, which is basically a plot of these equations, okay? These formulas, x and phi. Okay, that's all for today. Do you have any questions? Yes, there will be a formula sheet, but not much. Yeah, I will just give you the basic formulas. I might upload them, but it's not going to be very comprehensive. It will just contain the very basics. Okay. Yes, I will, you don't have to memorize the formulas I have written about. You can, I will give these formulas, for example. All right. If you don't have any questions, that's all for today. Let me stop the recording.